In this video, I want to talk about different ways to compress your neural network models so that they are small enough to run in embedded applications. Let's say that you've trained an awesome model that does a great job of predicting accurately, but as is often the case with the small size and compute capabilities of embedded processors, your model is just too big to fit on the device, and so you've got to compress it, but ideally without losing much accuracy. So in this video, we're going to cover 3 tools that you can use to compress your models: pruning, projection, and quantization. And if you want to try all of this out yourself, we're going to be following this MATLAB example where we use these 3 techniques to compress a neural network by more than 94% without any loss in accuracy. Link to the example is below. I think this is going to be pretty interesting and insightful, so I hope you stick around for it. I'm Brian, and welcome to a MATLAB Tech Talk. Alright, to begin, we have to talk about why some neural networks can even be compressed in the first place without much loss in accuracy. And the reason is that many networks are overparameterized. That means that they have more weights and connections than they actually need for accurate prediction. Now, how do they get this way? Well, sometimes this comes from just you choosing a larger architecture at the beginning of the project, just to be safe. You might not know the optimal size of the architecture needed to capture the relevant dynamics of the system. And so you go with something large, and then through compression, find out later that it could actually be smaller. Or maybe you're starting from another existing model, one that was well sized for its original purpose, and then you use transfer learning to adapt it to your problem. And in that case, perhaps a lot of the original model's capacity just isn't doing much for your particular task. And so in these cases, that excess structure is making the model larger than it needs to be, and we want to remove that structure in a systematic way. And that's where pruning and projection come in. And then we can reduce the size even more by storing the model's parameters and doing the inference calculations in a less precise format by quantizing the model. Like instead of 32-bit floats, we could use 8-bit integers. And so those are the 3 compression techniques that we're going to walk through in more detail in this MATLAB example. Now, before we can compress a model, we need to get a model. And that's what we're doing here in part 1. This example learns a model that uses acceleration data to predict if a car is driving over cracked pavement or not. So we have a bunch of these acceleration time series that are about 600 samples long or so of both not cracked and cracked pavement driving. And then down below, we use that to train a deep neural network. And you can walk through this training part on your own if you're interested, but we're just going to jump straight to part 2, which is the part that we're interested in, compressing the trained model. So let's open this up in MATLAB and walk through it. The first thing this example does is load the network if it doesn't already exist from part 1. And I also want to mention here that you can also load in a network that was trained outside of MATLAB, like with PyTorch, and then use MATLAB to compress and test the network. Okay, so now that we have a network, we can view it in the Deep Network Designer app, and then under the Compression Analyzer button, you can get more information about compressing the model. And this normally takes a few minutes to run, but I'm speeding it up here. All right, so here we go. This model currently has 14 layers, around 1,500 parameters, and takes about 6 kilobytes of memory to store the learnable parameters and state parameters of the network on disk. And this app estimates that we could compress this model up to about 83% with pruning alone, or 78% with projection alone, or 73% with quantization. And we can combine these techniques for even greater compression. Also, not every layer type supports every compression method, but the tool also shows you here what's available. All right, let's close this and set a baseline for the original model. This function testnet checks how well the original model performs with the test data, and we're getting just over 97% accuracy. So that's our starting point. And the question is, can we keep this number high while compressing the model? And we're going to start with pruning. Pruning finds the parameters that have the lowest impact on network accuracy, and then we remove them. And there's 2 ways to prune. We could do unstructured pruning and structured pruning. Unstructured pruning cuts individual weights in the network. So that is, it gets in and removes some of the connections between the nodes. And one way to do this is magnitude pruning, where the lowest magnitude weights are the ones that get removed. Higher magnitude connections here in my network are darker, and then the lower magnitude connections, like this one here, are lighter. And so when I prune this network, I am removing these lighter connections. And this approach is basically saying that if the magnitude of the weight between the two nodes is low, then it's probably not contributing as much as the higher magnitude weights, which is why they can be safely removed. And this is certainly a straightforward approach, and in general works really well because typically those weights are small because during training it learned that they don't have a large impact on the loss function. So keeping small weights is almost the same as just removing them completely. But the downside is that this creates random sparsity throughout the network. Instead of removing whole sections of the structure, it's just going through and thinning out some of the parameters. But those parameters are sort of still there, they've just been zeroed out. And this means that the size of the network hasn't really changed. The size of the matrices that make up the neural network, there's just more zeros in those matrices. And the problem with this is that unless your hardware is set up to specifically take advantage of sparse matrices, then you don't really get much speed or memory savings by doing this type of pruning. And this is especially true in embedded applications where the processor and the software libraries aren't usually optimized for sparse mathematics. So this brings us to the second approach, structured pruning. In structured pruning, we remove bigger pieces of the network, like entire filters or neurons. And not only does this reduce the number of parameters in the network, but it actually reduces the size of the matrices and therefore the number of calculations that are done. One popular method for structured pruning is called Taylor pruning. And basically with Taylor pruning, we estimate how much the loss function would be affected by removing a given part of the network. So we temporarily remove a section, check the change in the loss function, and then move on to temporarily removing another part of the structure. Afterwards, we assess all of the potential changes to the loss function and then remove the parts of the structure that have the lowest impact. It's smarter than just looking at weight magnitudes. It's actually considering the impact on performance. Also, instead of going through and removing a bunch of the structure all at once, often we'll do iterative pruning. We remove just a little bit of the lowest performing structure and then fine-tune the model again, which can change how the network relies on what is left. Then we do Taylor pruning again and remove another small section, and then we fine-tune again, and so on until you reach your accuracy or your size goals. And this can be much more accurate than just hacking off a large portion of your model in one go. So with all of that in mind, let's now go back to the MATLAB example where we can prune our network using this approach. This example uses Taylor pruning to remove a stated goal of 50% of the structure. So we're asking it to remove 50%. And the way it does that is it's going to iterate between those two steps. The first one determines the Taylor score for each prunable section of the network, and then it temporarily removes the least important parts. Then it retrains the remaining network. And then it keeps iterating between these two steps until the pruning goal is met. And then at that point, it does one final retrain of the whole network. And so if we scroll down here, we have this while loop that runs as long as we haven't met the pruning goals yet, and there are still sections of the network that can be pruned. And then this for loop here iterates between pruning and fine-tuning. So let me run this real quick, which should take a few minutes, but I'm going to speed it up so we don't have to wait around. And then in this next section, we're going to do the final retraining, which again, I've skipped over for time. So here we have it. We have our network, which is 50% smaller. And again, we'll check the accuracy against the test data, which surprisingly is now 100% accurate. But I wouldn't read too much into this number being better than it was before, since the test data is only like 30 sets, so it's probably like accurate to within a few percentage points. And in fact, if we run this network against the validation data, we can see that we're actually about 94% accurate here. So, in general, this smaller model is about as accurate as the larger model was. All right, so let's move on. Pruning is a great first step, but to compress the network even more, we turn to projection. And we can think of projection a lot like pruning, but with a twist. And that twist is that we first rotate the layer we want to compress to look at it from a different perspective. That rotation is the projection part. It reveals redundancies in the network that we couldn't see before. And the way we do this projection is with principal component analysis, or PCA. And if you're not familiar with PCA, the concept is pretty cool. And I think a simple visual example will help explain it. Let's say that we're analyzing acceleration data. So we have these series of data points over time. And from the example, each set of data consisted of hundreds of points. But for simplicity, let's just look at two sequential acceleration data points. So this is now two-dimensional data, and we can plot it on a graph. The first acceleration value can go on the x-axis, and the second value on the y-axis. Now we repeat this with more samples, and we can build up a scatter plot. And so what we want to try to do now is classify these data points into either cracked pavement or not. And at first glance, both axes seem useful for this classification, right? I mean, there's decent variance in the data in both directions. So it looks like we can't get rid of either axes since there appears to be valuable information in both. But what if we rotate the graph and then we draw new axes? Now we can see that with this new coordinate frame, the data varies mostly along this single direction. In the other direction, the data barely changes. It's pretty much all the same value. And so that means most of the information is actually captured along just this one axis. And because of that, we could probably safely remove the data in the second axis. So now we've gone from two-dimensional data down to one-dimensional data without much information loss. So that's what PCA does for us. And here's how it works. Let's start back at the original data. So now first we average all of the points in our data to find the center, and then we move everything so that the center is now at the origin of the coordinate frame. We're basically removing the bias in the data so that we can calculate the variance. Now we find the direction with the most variance, or in other words, the direction where the data is the most spread out. This is the first principal component. The second principal component must be orthogonal to the first and capture the next most variance. Now, for two-dimensional data like we have here, the second axis is fixed by the orthogonality constraint, but for higher order data sets, this isn't true. For example, with three-dimensional data, the first principal axis is still the direction of the highest variance, but then the second axis has to be orthogonal to the first, but it can rotate around it to find the next highest variance. And then here it's the third axis that is fixed completely by the orthogonality constraint. And if we had 600 dimensions like we do with our acceleration data, then we do this process 600 times across 600 axes. All right, so getting back to our data, the variance along axis 1 is 3.82, and the variance along axis 2 is 0.02. That means that axis 1 contains 99.5% of the total variance. Therefore, if we ignore axis 2, then we're still keeping over 99% of the unique information in this data. And with higher dimensional data, it works the exact same way. Each axis is ranked by how much variance it explains, and then we just decide how much variance of the total we want to keep, say like 95%, and then we ignore the rest. That's projection compression, where we are removing axes that don't contain much information. And we can apply this idea to neural networks. Here we can take this longer data sequence and feed it into a multi-layer network where it classifies the sequence into one of two labels. This network has 220 weights, or connections between the nodes, but we can reduce this number by choosing a layer, like this second layer, and then projecting it into a new subspace using PCA, like we just talked about. So we have this new subspace, and these are ordered based on how much variance there is in the data, or how well that subspace of network activations can capture the underlying features of the data at this point in the network. Now, this increased the number of connections to 284, but only temporarily, because we can now start to trim the low variance structure. reducing the overall number of learnable parameters while still accounting for the majority of the variance in the data. In this way, we've added an additional layer into our network, but we've reduced its overall size. Okay, so let's go back to MATLAB and compress the network even more with projection. And we're going to start by stating our reduction goal and then which layers we want to project. And here we're choosing 2 convolutional layers and 2 fully connected layers. And then we're using this function to project those layers using PCA and then removing the portions of the network that have the lowest variance. And just like we did with pruning, we now retrain the network with this new structure. Again, I'm skipping the training process because it's going to take a minute or 2. But now that that's over, we can test the new network again, and we can compare the accuracy and the size of the network across all 3 different variations. And as we can see, the accuracy has stayed pretty much the same, but the size of the pruned and projected network is about 1/4 of the original. So this is how we can go about removing all of that excess structure from our networks. But to compress the size even more, we can do one more thing, and that is to quantize the network. The concept of quantization is pretty easy to understand, but we do have to be careful with its execution. So let's start with what it is. We often train our models using high precision data types, like 32-bit floats. And this level of precision might not be necessary for the network to accurately classify incoming data. So we might be able to get away with reducing the precision of the data type so that instead of 32 bits per parameter, we only use, say, 8 bits. And this obviously can compress the size of the model by a factor of 4, but also, depending on your specific embedded processor, running 8-bit integer calculations can be faster than the equivalent 32-bit calculations. So there is potential speed up in the time it takes to do inference with a quantized network. Now, the difficulty in quantization comes from the fact that an 8-bit integer can only represent 256 different numbers. Therefore, we have to determine the range of numbers that our model needs so that we can make the best use of those 256 possibilities. And let me quickly explain with this simple visual. Let's say that this blue curve represents all of the different numbers in our network. That's both parameters and activation values. So this means that we've run the network with a bunch of different inputs, and this is a representation of which numbers show up during those calculations and how often. And this line is practically continuous, right? Because with 32 bits, we can represent over 4 billion numbers. However, when we quantize the data down to 8-bit, like I said, we have to map those numbers just to 256 bins. Now, for this visual, I'm just showing 10 bins, but hopefully you can imagine what 256 would look like. And the thing to note here is that all of the numbers between 0 and like 0.75 would all map to this first bin, which is where our loss of precision is coming from. Now, this yellow line over here represents the range of our data. And during quantization, we want to know pretty accurately where this line is. Because let's say that when we're mapping our data to an integer, we incorrectly think that the range stops here. This means that there's going to be clipping of every number above this line since we have to map it to the largest integer value we can, which just happens to be all the way down here. Now, on the flip side, if we think the range is larger than it actually is, then we're wasting valuable bins for areas that don't actually contain any numbers. This lowers the overall precision of the numbers that we do have. So with that in mind, let's go back to MATLAB one final time and quantize our network. In this section, you're going to see that there are 2 main functions that we're running. The first is the calibrate function. This is exercising the network with sample inputs and collecting the range information. It's finding where that yellow line should be. The second function, quantize, is returning a quantized neural network based on the range information that we got in the previous step. And then once again, we test the accuracy of the quantized network. And finally, we get to the end where we can see how much smaller the pruned, projected, and quantized network is while maintaining about the same level of accuracy. I recommend that you go and try this example out yourself, and especially if you have your own trained neural network for your project, it would be super interesting to go through this process and see how much you can compress it. All right, so this is where I'm going to finish this video, but I do want to call out that you can take this example further. In the next section, we go through this compression steps again, but this time we use the experiment manager to systematically figure out what the best compression ratio is between pruning and projection. That way you don't have to specify the reduction goals yourself. And then in the last section, we show how you can generate a Simulink model from your compressed network, which from there, you can then generate C code for your particular embedded processor and actually run it on the hardware. So it's all pretty cool stuff. All right, well, thanks for sticking around to the end of this video. And if you enjoyed this explanation, you can find all of the Tech Talk videos across many different topics, nicely organized at MathWorks.com. Thanks for watching, and I'll see you next time.